Hello everyone, welcome to lecture 56 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on tunable metamaterial based sensors. Here is the lecture outline. We will first discuss about the challenges of conventional sensors, and then we will focus on tunable metamaterial based sensors with an introduction to sensing principle using tunable metamaterials, and we will discuss about refractive index sensing using metamaterials. Then we will look into tunable metamaterial based biosensors in the gigahertz and microwave domain. We will take up some example of tunable high Q metamaterial based temperature sensing, and then we will also take up one example from the optical frequency domain where we will discuss tunable infrared metamaterial based biosensor. So, let us first focus on the challenges of conventional sensors. First of all, their performance are typically fixed because they have a fixed operating frequency and sensitivity. Then the conventional sensors have environmental interference, that means they are susceptible to noise and interference that impacts their accuracy. Moreover, the scope of a conventional sensor is limited because a single sensor will not be ideal for detecting a wide range of analytes or for different operating conditions. And then we need sensors that can, with this kind of problems, you can understand that there is need for active control. That means we need sensors that can adapt to their environment and the properties of the sample that is getting measured. So, with that we introduce metamaterial based sensors. All of you know that metamaterials are basically artificially engineered structures with sub-wavelength unit cells. And a quick recap for this is that the electromagnetic property or the response of these metamaterials are determined by their structure, not their chemical composition, right. So, when you talk about tunable metamaterials, that means these metamaterials basically integrate some active materials whose electromagnetic properties can be dynamically reconfigured. Okay. So, you can think of stimulus like thermal, something like phase change materials, okay, or electrical, that is where you can give some bias control, something like in liquid crystals or graphene, or you can think of mechanical, something like MEMS based geometry change. Okay. So, these kind of things will give you multifunctional and reconfigurable device performance. So, why they are important in sensing? Because advanced sensitivity via strong field confinement and resonant effects will basically improve the sensitivity and the detection of the analytes, right. And real time adaptability is also very important, where you can cater to different analytes and environmental changes. So, the typical applications could be in biochemical detection, environmental monitoring, IR spectroscopy and wearable sensors. So, the combination of metamaterials, resonance, selectivity and tunability can give rise to ultra sensitive versatile sensing platforms. So, there could be different tuning mechanisms. So, you can actually look into this figure that tells you about phase change materials, something like GST or VO2, where you can actually have optical or electrical heating that is acting as a stimulus and changes the property. You can think of semiconductors like transparent conducting oxides like ITO, AZO or silicon, where you can have optical or electrical pumping. There the free carrier density will change, and that basically changes the interband transition and the electrical or optical properties. You can think of liquid crystals where electrical biasing can change the molecular orientation and you can get the tunability. You can also think of solid dielectrics like barium titanate or lithium niobate, which are giving nonlinear optical response or thermo-optical response based on electrical and thermal biasing or pumping. There are other kind of materials which are also sensitive to magnetic fields, and then there are materials which are sensitive to mechanical stress, something like polymers, graphene or MEMS, which can undergo spatial deformation to give you a tunable property. So, of this, these are a couple of popular ones like liquid crystals or macro electromechanical systems or MEMS or phase change materials, which are basically showing, this one are basically showing temperature driven phase transitions, right. There is another material called GST Okay. So, that is also suitable for thermal sensing and switchable absorber kind of applications. So, with that we can think of different sensing mechanisms where you can apply tunable metamaterials. The first one would be the refractive index sensing. So, here what happens when there is a change in the refractive index of the analyte that you are going to sense, the resonance frequency of that metamaterial structure will basically change, and you can detect the change and correlate back to the change in the refractive index of the analyte. You can also get active tuning with the help of active stimulus like MEMS, thermal and liquid crystals, which you have seen. So, that basically giving you dynamic control, and that enables rapid reconfiguration for multifunctional sensing. So, here is a chart that shows metamaterials in biosensing applications. They can be done in gigahertz domain, that is basically for the RF and microwave. You can also do it in the optical frequency domain, that is in near infrared to visible frequency range. So, in the gigahertz domain, what is the mechanism? You typically look for split ring or complementary split ring resonator resonance. You look for spoof plasmon, surface plasmon polaritons, or high Q transmission line or cavity modes, and also you look for chiral or polarization sensitive responses. In the case of optical frequency domain, you look for localized surface plasmon resonance, phaneresonance, hyperbolic dispersion and chirality. So, in this case the tuning in the gigahertz domain, the tuning can be obtained using varactor diode, liquid metal or Farad bias, whereas in the case of optical domain you can use phase change material like GST or VO2 for refractive index tuning. So, now let us go into details of sensing principle using tunable metamaterials. So, we understood that metamaterial sensors basically rely on resonance. So, the sensor's resonant frequency is typically highly sensitive to the changes in the surrounding environment, particularly to the refractive index of the analyte. So, what you can do, the way the sensing works is that an electromagnetic wave is incident on the sensor. The presence of a sample basically changes the effective permittivity or the refractive index near the meta atoms of the metamaterials, and this change will shift the sensor's resonant frequency, and you can measure the shift in the frequency and correlate it to the properties of the analyte. Okay. So, that is how the sensing is done. Now, what is the advantage of the tunability? So, active tunability basically allows the sensor's resonance to be optimized for a specific analyte or to compensate for any kind of environmental noise, dramatically improving the precision and the performance of your sensor. So, if you look into the modeling aspect, the resonant frequency for SRR based metamaterial can be calculated using Drude-Lorentz model. So, here is the resonance frequency of an electromagnetic response, which is modeled as LC network. You can take it as 1 over square root of LC, and then with the geometric parameters of the split ring resonators, you can correlate those. So, here some example would be like, imagine the split ring resonator. Okay. So, there you will have a capacitance which is coming from the gap of the split ring. Okay. So, that basically acts as a parallel plate capacitor, where the capacitance can be taken as epsilon naught, epsilon c, WD, that is the width, and G is the gap. You can also get an inductance because there is a ring current which creates an inductance similar to that of a solenoid, and the inductance can be given as L equals mu naught A square by D. So, A is basically the radius and D is the thickness. Okay. So, with that you can see that according to this equation, the resonance frequency of the metamaterial is basically dependent on the inductance and the capacitance of that structure of the meta atom. And we have also seen that this L and C are basically depending on the physical parameter and the permittivity of the material that you put in the gap, that is epsilon c. Okay. So, all these parameters like SRR size and line width and the gap, thickness of the metal, all these things are playing the role in deciding the resonance frequency. Okay. So, what are the simulation method for this kind of metamaterials? You can do the simulation by varying the dielectric constant of a material with a fixed thickness. So, from that you can obtain what is the refractive index of your analyte, that is a function of the dielectric constant epsilon r given by square root of epsilon r mu r. So, really normally for most of the materials relative permeability will be taken as 1. So, n will be simply square root of epsilon r. Okay. So, the sensing performance matrix, performance is basically quantized using these key matrices. The first thing is the Q factor. So, it is basically a key indicator of the performance of the sensing. So, it is calculated as f naught, that is the central frequency or the resonance frequency divided by the full width of half maxima. So, if you normalize your resonance, you can find out the minus 3 dB bandwidth for that, and that will give you Q factor. And then you can calculate the sensitivity, that is basically the change in the resonance frequency per unit change in the refractive index, that can be written as delta f over delta n, which is proportional to delta f over delta epsilon r, and typically the unit for sensitivity will be hertz per refractive index unit. The final figure of merit FOM will be simply Q into S. So, when you have a higher figure of merit, it indicates that you have a better sensing performance, because it signifies a sharper and more detectable resonance from a given frequency shift, right. So, with that we move on to discussing the tunable metamaterial based biosensors, particularly for gigahertz domain. So, we will see a tunable high Q metamaterial based temperature sensing here. So, these high Q metamaterial units are in demand for precision sensing applications based on liquid metals. So, you see you are using mercury here. So, most exciting high performance sensors basically rely on dielectric or magnetic property changes of the substrates or superstrates. So, here is one sensing metamaterial unit based on thermally tunable liquid metal, that is mercury. So, as you can see, this metal mercury is known for its thermal expansion properties, and that has been used for making this unit cell. Okay. And it is basically in the form of a split ring resonator. So, you can call this as mercury split ring resonator, and there is a glass tube. Okay. So, you can also model these as an effective equivalent circuit model. So, you have this capacitances modeled here, inductance, and also the resistance. So, this is the effective circuit model for this mercury based split ring resonator. Now, this mercury based split ring resonator, which is introduced last time, shows magnetic resonance behavior. It can also show negative permeability frequency band shifts under different temperature, and the sphere that is having radius larger than the cylinder made of mercury is also used there to amplify the thermal expansion effect for the metamaterial. So, you can see that this is based on a principle that a larger unit volume, that is V naught of mercury, will lead to a more significant volume change delta V for a given temperature change delta T. So, you can actually write the thermal expansion coefficient of the mercury as gamma, which is 1 over V naught, the initial volume, times delta V divided by delta T. So, that turns out to be 0.18 into 10 to the minus 3 per degree centigrade. Okay. So, V naught is basically the initial mercury volume, and delta V by delta T is basically the volume change when the temperature basically varies by delta T. So, based on the split ring resonator design and the parameters, as you can see here, okay, you can calculate the mercury bar length that will change inside the glass tube with temperature, that can be given as delta L, which is basically given by this formula. This is reported by this work published in Optical Express. So, here you see that delta L is basically depending on this D3, D1 is basically the diameter of the cylinder. Okay. L naught is basically the initial length of the mercury in the cylinder, okay, and delta T is basically the temperature change. So, if you want to read more about this work, you can go and visit this paper, you will have all the information, but I am just showing you that how different mechanisms have been applied to make a high Q sensor. So, here the resonant frequency shift is basically due to the temperature change, that is delta T, okay, and then you can see that delta omega is given as square root of 1 over L delta T, that is basically the inductance that is changing because of the change in temperature, that is now getting added to the initial inductance. Similarly, there is a change in the capacitance that is getting added to the initial capacitance. So, this is the new resonance frequency, this is the old one, and that is basically giving you the change in the resonance frequency delta omega. So, with that, if you see the simulation results based on this kind of split ring resonator, okay, you will see that if you vary the mercury bar length from 21.42 millimeter to 24.97 millimeter in a commercially available simulation software HFSS, and you see how the transmission and the retrieve permeability curves are changing, that is basically plotted here. So, what you can clearly see that when you change the length of the bar corresponding to the changing temperature from 0 degree to 57.7 degree, the resonance of the metamaterial is basically shifting to lower frequency, right. So, from here, so this is the hottest one, okay. So, you can say from here to here it is going, right, from 0 to 57.7 degrees centigrade, okay. Similarly, the permeability curve also shifts to lower frequency, and the resonance frequency shifted also shows a linear relationship with the temperature in the range of 0 to 30 degrees centigrade. So, that is a good thing, you can use that for sensing purpose. Okay. So, the simulated transmission and the retrieve permeability and the refractive index curves are basically shown. Here it is for the SRR, and here it is basically for the split ring resonator and a wire kind of structure. Okay. So, here again similarly the mercury bar length was changed and it was plotted. Okay. So, similarly we also see that in this case the resonance frequency is basically shifting to lower frequency. Further analysis also shows that the permeability and the refractive index curve, they also shift to lower frequency with the increase in temperature. So, finally, what is important is that if you see the resonance frequency shift with temperature, as we mentioned that over 0 to 30 degree, it is basically showing a linear fit, which is very good, and this is basically the sensitivity 7.2 megahertz per degree centigrade, that is the linear tuning scale factor that was obtained for this sensor, and the sensitivity was obtained to be 1.4 into 10 to the minus 7 degree centigrade per hertz. Okay. So, the Q factor and the figure of merit of this mercury based split ring resonator under different mercury bar length, which is basically corresponding to the temperature change amounts, okay, they are also shown in this figure. So, what we understood that the sensitivity can be further enhanced with larger mercury sphere and thinner mercury bar, because that is there in the equation 1. So, the physical relation actually shows you that thing. So, the length, okay, is here and d1 is the diameter. Okay. So, with that you can basically change the, with temperature you can have more change in the mercury bar length. One is in the numerator, this is in the denominator, that is the diameter of the cylinder. So, with that we move on to the next topic, that is how we can design a tunable metamaterial based biosensor in the optical frequency domain. So, here is a schematic of a metamaterial cubic and a cylinder resonator. So, this is a structure, this is a gold based structure on GST associated structure, or it is a substrate basically GST, and you will see this part is basically the biomaterial which you are basically sensing, and your wave will be falling from the top. So, this kind of proposed metamaterial based biosensor, this work was reported in scientific reports, okay, by this set of authors. So, they have basically used this kind of thing for detection of hemoglobin and urine using phase change material that enables tunable optical sensing. Here the biosensor composition, as I already discussed, is made of a phase change material, which is basically GST with some alloy combinations. Why GST? Because GST changes phase with temperature, so it enables tunable sensing for biosensing application. Okay. So, you can see the design here, that the structure basically incorporates a cuboidal or a cylindrical gold resonator that is placed on this GST substrate, and GST here is used as a base material. So, it basically can change its phase with temperature from amorphous to crystalline. So, A is for amorphous, C is for crystalline, okay, and these are the dimensions of the structure. So, surface thickness is 800 nanometer, the height of the gold structure is 600 nanometer, the biomaterial one is like 2 micron or 2000 nanometer, okay, and then these are the structural dimensions. G1 and L are basically 1400 and 2000 nanometer. So, what they have done, they basically made biosensors that includes 3 different unit cells, something like UC1, UC2 and UC3. These are basically 3 different unit cells, similarly for the cylindrical one also, and these are the dimensions of each of these unit cells. Okay. So, overall you can see the overall size and G1, that is basically the inner structure, that is also changing. Now, why they have tried 3 different ones? Because each has a different size and that will affect the sensor's tunability. Now, to quickly remind what is the operating principle here. So, I need to understand the sensing mechanism. So, here the sensor basically detects the change in the refractive index of an analyte, that can be hemoglobin or urine, by measuring the shift in its absorption peak. Now, tunability is coming from the phase transition of GST, that is with temperature when it moves from amorphous to crystalline, that basically allows the spectral response to be tuned. Also, the number of resonators in the array provides tunability for both amorphous and crystalline GST based biosensors. Now, we can observe the response in the optical behavior. So, if you want to measure the absorbance, that is basically A, which is 1 minus T minus R. T is the transmittance and R is the reflectance. So, what is not transmitted and reflected is basically getting absorbed. You can also discuss this from the impedance matching theory, that for maximum absorption what you want, you do not want any reflection, right. So, when the impedance of the free space and the device is matched, there is no impedance mismatch, there is no reflection. And for this case, the overall transmission can be reduced from T equals e to the power minus 2 n 2 d k to e to the power minus alpha d. So, here k is basically the free space of propagation vector, d is the thickness sample or thickness of the sample, and n 2 is the effective refractive index. So, you can see all these details in this paper as well. I am telling you that here the final goal is to demonstrate how the sensing performance looks like with metamaterials. So, we will see that the transmission basically decreases exponentially with the thickness and the absorption coefficient alpha, okay, and the value of the effective refractive index N2 is basically determined by the refractive index of the spacer material, which is here GST. So, when you change the GST phase from amorphous to crystalline, there is a change in the refractive index, right. So, if you achieve large effective refractive index N2, that will basically enhance the absorption efficiency, and to achieve a near unity absorption, your N2 should be as large as possible. So, with that we will go for the sensor performance testing. So, the sensor built with amorphous GST, AGST or crystalline GST, okay. So, we will have different structural designs. So, when you do the testing with varying biomolecular concentration, say let us consider hemoglobin 4 different concentration and urine of 4 different concentration. This is how the refractive index of the hemoglobin and urine in the different concentration look like. So, you see there is a steady increase in the refractive index with the concentration. Similarly, you can also see that here. So, that will basically, if the refractive index of this material changes, that will alter the optical performance, and that is how the sensing is done. So, this was reported through simulation. The sensors performance was numerically investigated using FEM method. So, they put periodic boundary condition along x and y direction. So, it is kind of a very large sensor they made, okay, because they have put periodic conditions here, okay. And then they have put T transverse electric mode excitation, okay, for the IR incidence along the z direction, and they also considered a metallic layer at the bottom to completely kill the transmission, so that absorption increases. So, here is the simulation result for different unit cells. So, it shows the absorption spectrum, okay, for different concentration of molecules. So, this is having AGST and this is having CGST as the substrate. So, you can see they behave differently because they also have different properties, right. Similarly, for different unit cells, UC2 also you see similar kind of observation. For the left one is with AGST as substrate, the right one with CGST as substrate. Okay. So, this is for the unit cell 3, the 3 unit cells we have described, similar kind of observation. So, what you see here is that finally, when you plot the refractive index and the wavelength, so this is how the the absorption or the spectral response is basically shifting. That means, the absorption peak basically keeps shifting with the change in refractive index. So, you can see for the two cases of, so the blue one is for the amorphous, the other one is for the crystalline CGST. So, you see that for in this case they are almost equal, the shifts, but it is very different when you are in this particular range. Okay. So, this is 1.57 to 1.6 and this is the range of the refractive index that is being changed. Similar observation is also here. So, they all tell you about the urine based sensing, this one, and this is for the hemoglobin based sensing. So, another difference is that here you are using the cylindrical structures for sensing and here you are using the square unit cell structures for sensing. So, the top row is basically for the urine detection, the bottom row is doing the hemoglobin detection. So, what you see here, that the sensitivity of the biosensor basically determines the detection capability of the sensor, and if you calculate the cylindrical resonators have for urine, it reported 1000 to 2333 nanometer per refractive index unit, whereas the sensitivity in the case of hemoglobin is lower, it is from 825 to 1795 nanometer per refractive index unit. Okay. And for the cubic ones, okay, so this is basically the comparison between the cylindrical for urine and cylindrical for hemoglobin. If you come to the right figure, the cubic resonator for urine gives even better sensitivity, and it is also giving much higher, not much higher, little bit higher for the hemoglobin as well. So, a quick comparison tells you that the cubic ones, the cubic resonators have better sensitivity as compared to the cylindrical one. So, with that we conclude this lecture, and if you have got any query regarding this lecture, you can drop an email to this email address. Thank you.